Hi everyone, this is just a walkthrough of your end of year exam paper. The first paper, this is the multiple choice part of it. Your work for the lesson really is to make sure that you've watched this lesson either live or recorded. And if you've recorded it, what you might want to do, as I'll be posting it straight away on to show my homework, what you might want to do is to then play it again so that you can then sort of go through the various questions where you still don't quite understand. And it'll just help you to not so much know what the answers were, because obviously I've marked it and you've had feedback on that, but also to make sure that you know why you got certain answers wrong, or where if you know for a fact that you've actually guessed an answer, you know why it was the answer. Okay, so we're just going to go through it in order of questions. I'm not going to spend ages on this. I think short and sweet's the order of the day today. So you've obviously got your formula sheet. Go past the formula sheet and we start on question number 1. Now, question number 1 is all about estimates. They put a dot here. What I think this was a printing error caused by the system I used to download and edit it. And I do apologise for it not being quite right, but that should be times. So you're looking for one that's not a reasonable estimate. Well, that one, the atmospheric pressure, that's about right. It's 1.01 times 10 to the power 5 pascals, depending on the weather. Light takes 5 times 10 to the power 2 seconds. Well, if you sit and calculate that, that's more or less about 8 minutes, which is what it takes. Frequency of ultraviolet light, this one's a little bit harder. You might want to try to think about about calculating the wavelength. As you know, the wavelengths of ultraviolet light are going to be to the order of about 10 to the power of minus 8 meters or so. But it's a difficult one to remember, so we'll come back to it. This one, the lifespan of a man is 2 times 10 to the power of 9. So what you do is you say, well, 2 times 10 to the power of 9. You divide that by 3,600 seconds in an hour. Divide that by 24 hours. Divide that 24 hours by 365 days in a year. You end up with something like 63 or 64 or something like that, which is about a good estimate. So C is the one that's not a good estimate. It is quite a way out. Next one is all to do with base units. 3 of these quantities have got the same unit. Which one doesn't? So energy over distance. Well, energy is force times distance, so that's going to be the dimensions of force. Force obviously is going to be dimensions of force. Power times time, that's energy. That's not force. So C is probably the answer, but just to double check, rate of change of momentum, well, that in Newton's second law of motion is a good definition of force. So it's got to be C. Then it says, which group of quantities contains only vectors? So that's a scalar, so that's no good. Next one, work. Ooh, work is energy. Work is energy, so that's not right. That's a scalar. All the rest are vectors. Displacement, force, velocity, they're all vectors. Power, electric field strength, or power is a scalar, so it's got to be C. The next one's all about scales and calibration. So an ammeter is calibrated so that it shows a full scale deflection when it measures a current of 2 amps. So in other words, that's 2. So assume it goes up linearly. So from 0 to 2, that's going to be 2, 0.2, 0.4, 0.5, 0.6, 0.7, 0. Is that working? No, that doesn't work, does it? 2, 4, that's 6, 8. 1.0, 1.2, 1.4, 1.6, 1.8, and 2.0. Okay, so if it's pointing somewhere halfway between 1.4 and 1.6, a good estimate for the ammeter reading is going to be about 1.5 amps. Okay, another way to do that is just to do it very, very visually. If you know that full scale is 2, then you know it's going to be somewhere between 1 and 2, because 1 would be halfway along. So the only one that's between 1 and 2 would be B. It's another way to do it. Okay, on to the next one. Question number 5. The width of a table is measured as 50.3 plus or minus 0.1, and its length is 1.4 plus or minus 0.01 meters. So you've got to be careful. This is in centimeters. So the first thing we've got to do is work this out in meters. So that would be 0.503 plus or minus 0.01 meters. Okay. It then says you've got to work out the area of the table and its absolute uncertainty. So if you multiply those two together, you get 0.704. Okay, I'll just double check that. Yep, 0.004. But what you've got to do is then work out the uncertainty of both. And there's two ways of doing it. One is to work out the upper bounds. The other one, so you can work out the upper and lower bounds in each case. So that you know is 0.503 times 1.4 is equal to that. So you work out the upper bound of the area. That'll be 0.513. Got that right? No, it's not going to be quite right, is it? Because that's going to be plus or minus 0.1, so that'd be 0.01 meters. So it's 504 multiplied by the upper bounds here, 1.41. Okay, and then you work out the lower bounds, 0.502 multiplied by 1.39, and that should give you a range. Okay, so you subtract the two of them together and you know that the uncertainty is the range over 2. Okay, so it comes out to be B. The other way to do part B, and I will take a bit of time just to show you this because it is good practice to know how to do this bit, to do it another way. Another way to do part B is to work out the percentage uncertainties, because the percentage uncertainty in the area is the percentage uncertainty in the width plus the percentage uncertainty in the length. Okay, so that is the uncertainty. So to get the percentage uncertainty, get the full uncertainty in the area, which is what you've got to try and work out, you end up with the area multiplied by the two percentage uncertainties added together. It should come out to be about the same. Okay, so that's two different ways of doing the same thing. Right, moving on. Got number 6. You've got a stone is projected horizontally at times t equals 0 and falls. We're going to ignore air resistance. And the stone has a horizontal component of velocity and a vertical component. How do they vary with time? Right, so remember your projectiles. The simplest way to think about this is think about it in terms of projectiles. We know if you've got an object and it's got a horizontal velocity and a vertical velocity, we know that if there's no air resistance, that's just going to be constant. Okay, and indeed they are all labeled as constants, and VV would be acceleration times time. So we're looking for a straight line through the origin where the vertical component of the velocity is increasing linearly, and where the horizontal component of velocity is the same. So this one's obviously wrong because that's got VV, so that's not it. Now, here we're looking for a linear increase, so it's A. Okay. It's not B. Sorry, it's not B because they've got the two swapped over. It's not C because there you've not got a constant acceleration. We know the vertical velocity will be constant. The acceleration will be constant. The horizontal velocity will be constant. We know again here it's not going to be a curve, so that's clearly wrong as well. So the next part is question 7. You have 2 isolated spheres with a mass of 2 kilograms and 4 kilograms respectively. Their spheres collide and move apart. During the collision, 2 kilogram mass has an average acceleration of 8 meters per second squared. Well, we're looking at Newton's third law of motion, believe it or not here. A lot of people won't recognize it until it's pointed out that if you've got 2 spheres in contact, the 2 kilogram sphere will exert the same force on the 4 kilogram sphere as the force from the 4 kilogram sphere on the 2 kilogram sphere. So if the 2 kilogram sphere has 8 meters per second acceleration, then if you've got double the mass for the same force, you're going to have half the acceleration. So the answer is B. It's half of 8, isn't it? So moving on to question number 8. Got a mass placed on a frictionless slope inclined at 30 degrees to horizontal. The mass is then released. What is going to be the acceleration down the slope? So we've got to think very carefully. Well, we know it's not going to be 9.81 meters per second squared for a start. So what we've got to think about is we've got to think about the component of the force, the component of the acceleration, which will be in the direction of the slope. So if we think about it, if you've got a slope at 30 degrees, you've got an object on there, you know that its acceleration downwards will be g, 9.81. So the acceleration, the component of g in that direction, okay, it's a little bit hard to see, so I can draw it bigger if I want to on my scrap paper. This acceleration will be there. So the component, the right angle component of the acceleration is going to be the opposite times the hypotenuse, g. So it's a triangle. So that's going to be g sine theta, which is 9.81 times the sine of 30 degrees. So that then will come out to be A as your answer. It gets about half. The sine of 30 is about 0.5. Number 9, you've got a parachutist falling vertically at rest from time t equals 0 from a hot air balloon. She falls for some distance before opening her parachute, which shows the variation with time t of the speed of the parachutist. So we're going to be thinking a little bit more about air resistance here. So as you fall as a parachute, you should be able to recognize this anyway from examples you've covered in classes, but we know we start off with a constant acceleration. Air resistance takes into effect, so the acceleration reduces. She reaches terminal velocity where the air resistance is equal to her weight. Then she opens the parachute. She'll decelerate quickly at first. As she slows down, there'll be less air resistance until the air resistance is equal to her weight again. So she reaches a new terminal velocity, and then eventually she'll hit the ground. Okay, so the answer has got to be A. You should be able to recognize that one straight away from your notes. Number 10, a ship has got a mass of 8 times 10 to the power of 7 kilograms. It's approaching a harbour with a speed of 16.4 meters per second. Using reverse thrust, it can maintain a constant total stopping force of 920,000 newtons. How long will it take to stop? So we've got to think about this very, very carefully. Well, the simplest way to do this is to know that force is the rate of change of momentum. If that's the case, the time is going to be the change in momentum over the force applied. So the change in momentum is going to be 8 times 10 to the power of 7, 8.4 times 10 to the power of 7 kilograms, multiplied by 16.4 meters per second, divided by 920,000 newtons, not 92,000, 20,000, and the answer will come out to be, well, it works out about 25 minutes. Okay, but that's how you do it. So that will give you it in seconds. Then you need to divide that number by 60 to get it in minutes. Okay, right, on to the next one. Number 11, you've got a rigid hollow sphere is immersed in deep water and released from rest. It experiences an upthrust which propels it towards the surface. Which one shows the variation in time with its upward velocity? Well, if it's going to be, we've got to think a little bit carefully about it. It's immersed in deep in water and released from rest. It's not just pushed just under the surface. So it's going to be actually a terminal velocity question, because it's going to be due to the dynamic resistance from the water. So it will start off accelerating upwards, and eventually the friction with the water will decrease the net force until eventually it reaches a constant force at A. Pretty simple. So number 12, you've got a flat metal disc of radius r. Forces of magnitude F are applied tangentially at the edge of the disc. The forces are in the plane of the disc. Which arrangement of forces produces only a torque of magnitude 2Fr? So which of these produces a torque of a magnitude of 2Fr? So this one, well, only a torque. So this is not in equilibrium. There's going to be a net force in that direction. So that's not just producing a torque. This one, the linear forces are balanced, and it's F plus FR plus FR. That's going to be the correct answer there. This one again produces a net force in that direction, and this one produces a torque only, but that's 2F times R plus 2F times R, that's 4FR. So B is definitely the answer. On to question number 13. A diagram shows the jib of a crane, that's the bit that reaches outwards, at an angle of 35 degrees to the vertical. A cable passes over the frictionless pulley, carries a load of 1,830 newtons. The force R that the pulley exerts on the cable is in line with the jib. So that's going to be pulling in that direction. So it's going to be equal and opposite to the resultant between these two forces. It says it wants to know the value of that force. It says it's all in equilibrium. So you know that if you think about it, there are two ways of actually doing this. The simplest way, I think, would be to do this by scale diagram, by drawing a scale diagram and using a protractor. So you could draw a scale diagram. So let's do it that way. It's the simplest way to do it, I think. So if I just grab my protractor and my ruler, when you're drawing, you just got to think about a scale first of all. So my scale, well, if I've got 1,380 newtons each way, so 1,830 newtons each way, I think I probably want to do something in the region of about a 1 to 5 or something like that. So I could say that I could actually come up with the scale. I could say, well, I could say 1 centimetre is maybe 20 newtons. I think that's best. So if you calculate it, if you've got 1,830 and you divide it by 20 newtons, gives me 91.5 centimeters. Well, it's probably maybe we say 200 newtons then. Okay, maybe we say 200 newtons. So that's 1830 divided by 2. Oops, sorry, I've gone off the screen there. 200 gives me 9.15 centimeters. So the first one's vertically downwards, 9.15 centimeters. So I start off at 0 there, and I go all the way down to 9. Well, I'm going to say about 9.2. About there. Okay, so that's your first force. The second force you need to draw, well, you've got to work out what that is from the vertical. Well, if we think about it, if that's 180 degrees, that would be 70 degrees, so that would be 110 degrees from vertical. So I take my protractor and I work out what that is. So it's end-to-end arrows, remember. Take your protractor, you put your cross, you draw it as accurately as you possibly can. So 110 degrees from vertical is there. You can see that's 110. And I'm going to draw another line of 9.15 centimeters and hope I don't go off the end of my paper, which I don't quite, but I get very close to it. It's because I didn't plan properly. There's my 0 on there. I'll draw it as accurately as I possibly can. So my value just about fits on the paper. And then I just join up my 2 lines, because those are my 2 arrows. do it again as accurately as I possibly can, and I measure the length of the line. Well, I make that 14.8. Oops. I make that about 14.8 centimeters. 14.8 centimeters, which I'll multiply that by 200. Gives me 2,960. So I'm looking for an answer that's pretty close to that. So I would say that would be number 13 is D, 3,000 newtons. Now, the quick way to do this one is to do it by inspection. You know that the resultant force is going to be somewhere between the force from one of the cable, from one side of the cable, and the sum of the two forces on both sides of the cable. So you know it'll be somewhere between 1,830 and 3,660. So if you know that, you can actually eliminate the first two straight away. So even if you're really struggling with a calculation, you're really not quite sure what to do, you can actually get it down to 50-50, which is a lifeline on Who Wants to Be a Millionaire. So a unit for density is going to be a mass divided by a volume. So that's not a unit for density. That's not a unit for density because that's not a volume. Kilograms per square centimetre is not a unit for density. And grams per cubic millimetre, that is a unit for density. Okay, you should just know that. Then it says which statement about energy is not correct. So you either know this one or you don't. So number 15, energy is never lost, but it may be transferred between different forms. Well, that's correct. Okay, that's kind of the first law of thermodynamics. In an inelastic collision, the total energy is constant. Well, that's still true. A lot of people think that that's the answer, but that would be correct if that was the kinetic energy, but the total energy is always going to be constant. Don't forget, in an inelastic collision, some of the kinetic energy will be converted into thermal energy, but the total energy is still constant. So C, in the efficiency of a system is the ratio of the useful output to the total input. That's correct. So it must be D. When a machine does work, friction reduces the total energy. That's not true because you remember that the energy just gets converted into thermal energy. So the total energy stays the same. Right, the next one, electric kettle is rated at having an input power of 1.5 kilowatts and an efficiency of 65%. It is switched on for 2 minutes. It says how much energy is transferred to the water in the kettle. So we know straight away that energy is power times time. Now all of these are in kilojoules, so I'm not going to bother converting into joules. I'm just going to use 1.5. So the power is 1.5 kilowatts, but it's got an efficiency of 65%. So only 65% of that power goes into the water. So that's 0.65. Multiply it by 2 minutes. Well, 2 minutes is 120 seconds. And we end up with the answer of 117, which is the correct answer there. Okay, easy as that. So number 17, you're on a planet. The gravitational force F acts on a mass of 6 kilograms. The mass is moved by a force F of distance of 30 meters in the direction of the gravitational field. The work done by the field is 450 joules. What is the force on the mass and what's the acceleration due to free fall on the planet? So what are we doing here? So we're trying to work out the force and the mass. So we've got to work out G first. So G, well, we know that the work is mg times the change in height. You could put a delta in front if you want to be very, very precise about this. So you want to work out G. Well, G is going to be the work done over the mass times the change in height. So the mass is going to be, so the work done is 450 divided by a mass of 6 kilograms multiplied by a height of 30 meters. And that should come out to be 15. Okay, so it's either, so it's not A or B, it's either C or D. Then to work out the force on the mass, that's simply mg. So mg is 15 times 6. So the answer is, to get this right, double check. No, I've got that wrong. I've done that wrong. I do apologise. That's not 15 at all. So go back again. So it's 450 divided by 6 times 30. Get my calculator out. So it's 2.5. 2.5 is the answer. So it is definitely C. I do apologise. That was me having a slight senior moment, looking at the wrong numbers in my notes. Okay, so it's not equal to 15. It's equal to 2.5. I could tell you straight away the reason why I sort of stopped and stammered was I realised that was no way that was equal to 15, and actually that's more like 2.5. So number 18, a girl of mass of 50 kilograms runs up a flight of 20 steps in 7 seconds, and each step is 25 centimeters high. Her useful power output. So power is the work done divided by the time. So the work done is going to be mgh over time. Here the 8, so the mass is 50 kilograms. Now we're assuming we're on Earth, so that's 9.81. It's on your formula sheet. Multiplied by the height. So we've got 20 steps and 25 centimeters high. So 4 steps is going to be 1 meter. 20 divided by 4 is 5. So she's going to be going up 5 meters in a time of 7 seconds. So then you just calculate that, and the calculation should come out to be about 350-ish. Okay. Now again, you can use orders of magnitude. They're talking about somebody running up a flight of steps. Well, it's not going to be 2.5 kilowatts. That's several horsepower. That would be sort of sort of the power of a moped, really. And these two, to me, because I know the approximate correct values, these two to me actually smack of being just way too low. So to me, even just at a glance, I could tell you the answer was that, but it's always well worth doing the calculation. That way you know it's definitely the answer. The next question is going to be an experiment to measure the Young's modulus. Okay, so it's a Young's modulus question. We're measuring the Young's modulus of a wire of the metal diameter of 0.25 millimeters is clamped down. The wire passes from a clamp around a frictionless pulley to a second frictionless pulley where load F is applied to it. Okay. So it then says a marker is attached to the wire, so that the total length of the wire between the clamp and the marker is 3.7 meters. Okay. So we're maintaining a distance there of 3.7. Okay. So we have to be very careful here. It says it tells you that you've got a change in force versus the position of the marker. So the position of the marker is going to give you an extension. Now, there's a couple of ways of doing this. The simplest way to do it is to actually use the graph itself. You know that the Young's modulus is FL over AE, stress over strain. Okay, you ought to know that formula by now. Now, there's a little trick here. What we can do is what we've got here is not actually the extension. It's the extension from 4.5 millimeters. And yes, you could measure it here and sort of calculate it, but in reality, it would be nice to use the graph itself. So we could put extension as the subject, and we end up with L over A times the Young's modulus multiplied by the force. Double check it. Yeah, that makes sense. Multiply both sides by E. Okay, cancel it out from that side. Divide both sides by the Young's modulus. Cancels it out from that side. So we end up with that. And we know the gradient is LO is y equals mx. Okay, the gradient actually is going to be equal to that, because we know that even if you've got E plus 0 plus 4.5, actually that just becomes a plus C element, which you don't really need. Okay, so if we measure the gradient very, very easy. The gradient is from 4.5 to 8, so that's 3.5. Now let's start converting our units already. 0.0035. Okay, divided by 10. So the gradient is 0.0035 divided by the 10 newtons is equal to the length, which it says is 3.7 meters. Okay, it's 3.7 meters. The cross-sectional area, well, it tells you the diameter, so it's a quarter pi d squared. So we multiply that side by 4, and with pi times 0.25 millimeters, that's 0.00025 squared is equal to E. Whoops, I've gone off the bottom there. Okay. And from there, there's actually a gradient. That's this expression here. So you can rearrange to make E the subject, plug the numbers in. That's fairly trivial. And the answer should come out to be, according to my notes, it should come out to be D, 2.2 times 10 to the power of 11 pascals. Number 20, a scientist is investigating the properties of a new material. So he plots a force extension graph of the material up to its breaking point. So which statement must be correct? So looking for the correct statement. The area under the graph from P to R is the strain energy stored in the material. Well, not necessarily, because if it's gone past the proportional limit, then some of that energy will have been, some of that work done in stretching it will have actually, been lost as thermal energy. So that's not true. B, the area under the graph from P to R is the work done in stretching material. That's correct. So that is your correct answer right there. Right, the next one, a progressive sound wave in air has an amplitude of x naught and intensity of I. The amplitude was increased by 3 times x naught, so it's 3 times the amplitude. So it's the relationship between the amplitude and the intensity. So remember, the amplitude is proportional, amplitude squared is proportional to intensity. So if you've got 3 times the amplitude, you can have 3 squared times the intensity. So that's 9 times the intensity. Number 22, the variation of a distance of a transverse wave on a rope is shown. Time equals 0. You've got the frequency, 0.5 hertz. You're given the original, so it's a position displacement graph. And I'm just going to pause that to go and answer the door, because somebody obviously isn't doing that. Sorry about that. A little bit of a pause there for a second. Where was I? Yeah. So it wants to know the position of x at time is 1 second. So if it's 0.5 hertz, after 1 second, it's done 1 complete oscillation. Okay. So if you think about it, if it's done after 1 second, it's done 2 complete oscillations. So the answer to 22, well, let's think about it. Have we got this right? 0.5 hertz? No. 0.5 hertz implies a time period of 2 seconds, and it wants it in 1 second. So what I said was wrong. So I've got to think carefully. Think. This is half an oscillation. So x will have gone, an oscillation is to go from top to bottom to top. So it will be B is the answer. Number 23, got a sound wave detected by a microphone. The output's shown on the cathode ray oscilloscope. So this is an oscilloscope question. It tells you the time base is set at 2 milliseconds per division, and it wants to know the frequency. So what you're looking at is the number of squares between the two peaks here. You could do it at the midpoints, it's exactly the same. Technically, really, in the real world, we use the midpoints just because it's much easier to measure absolutely precisely. So we've got 1, 2, 3, 4 squares. So that's 0.2 times 10 to the minus 3 times 4 is 0.8 times 10 to the minus 3. And to get to then work out the actual frequency, it's 1 divided by that. So we know straight away, even before you've even done the calculation, you know it's going to be a number above 1,000. So we know if you actually do the calculation, it comes out to be 1,250. Okay, you can eliminate A straight away, even before you've actually done the calculation. But you do the calculation to get the frequency, and it comes out. Number 24, a bat flies directly towards a fixed ultrasound detector with a speed of 25 meters per second. It emits a pulse of ultrasound, a frequency of 40 kilohertz. The speed of sound in air is 330 meters per second. What frequency does the ultrasound detector record? Now it says it's flying towards it. So this is a Doppler question. So you need to go back to your formula sheet and find the formula for the Doppler effect. So our Doppler formula is this one here. The frequency observed is equal to that. So frequency observed is equal to the Fs times, where was I, times V over V. Now it's going to be plus or minus. Well, you can do this by inspection. It's flying towards it. We know it's a high frequency. Think of a car going past, meow. So higher frequency. So we want a lower common denominator. V minus 2. Vs. Okay. So we've got to think about it carefully. So that's going to be 40 kilohertz. Well, it's in kilohertz as well, so we might as well keep it there. 40 multiplied by 330 over 330 minus 25. And the answer comes out to be D, 43.3 kilohertz. Okay. Now you've got to be careful here. Where are pitfalls? Well, first of all, the first thing you can do, if ever you're completely stuck with this question, if you're really struggling with that, because I sometimes actually get confused between V and VS when I'm doing this myself. So it's quite natural to be completely stuck with using that formula. But you can do some inspection if you want to just guess between two answers. If it's emitting 40 kilohertz and it's traveling towards the ultrasound detector, we're expecting a higher frequency. So if it's a higher frequency, we know that these two are out straight away. Okay, and then the last one is just really a calculation. Number 25, you've got electromagnetic wave of the wavelength of 10 to the power minus 7 meters. So we're looking at something with a wavelength of the order of about 100 nanometers, which in each region, you've got to know your electromagnetic spectrum. In each region, that would be round about the ultraviolet light. The region diagram shows a stationary wave on a string. You've got 3 nodes. So which statement is correct? All points on the string is vibrating phase. No, because if that one's going downwards and that bit will be going upwards, so that's no good. All points on the string vibrate with the same amplitude. No, because this one will vibrate with an amplitude there, and this bit will vibrate with a much lower amplitude, and this will have an amplitude of 0. So that's not true. Points equidistant from N2 vibrate with the same frequency and in phase. Points equidistant from N2 vibrate with the same frequency and in phase. Well, we know they'll all be vibrating with the same frequency. They won't all be vibrating with the same amplitude, so C is the correct
First
answer,
lunch sitting.
even though the way they wrote
Students in
that really was
non-practical
quite horrific.
classes should go for lunch and return in 45 minutes.
So number 27, in which situation does diffraction occur? So diffraction occurs when a wave passes through a gap. So the answer is C. Sorry, 26, sorry, points equidistant from D. I do apologise. Equidistant from N2, in other words, same distance from N2, it's D up here. I do apologise, I was reading the wrong bit of my notes. The reason why they're not in phase is because if you look at it from N2, if you get 2 points equidistant, equidistant means equal distance. And this is where the wording is a bit strange. So if they're the same distance, this one would be moving, say, moving down like that. That one would be moving up like that. They'd have the same amplitude, but they'd be out of phase. So it's D for 26. I do apologise. It's reading the wrong part of my notes. Right, so which situation of diffraction occur? We've done that one. On to the next one. Right, so we've got two source interference by the looks of it, just by looking at the picture. Student connects two loudspeakers to a signal generator. As student walks from P to Q, he notices the loudness of the sound rises and falls repeatedly. What causes the loudness of the sounds to vary? Well, it's interference. That's dead easy. Actually, it looks like when candidates apparently on a survey, when they saw this question, they were quite concerned about it looking, about it being quite difficult, but actually it was really easy. So you've got a parallel beam of white light is incident normally on diffraction grating. The second order and third order spectra partially overlap. Which wavelength in the third order spectrum appears at the same angle as the wavelength of 600 nanometers in the second order spectrum? Blimey, that sounds awful. So what it's saying is the second order and third order partially overlap. So the third order is when n is equal to 3. So we use in the formula n lambda equals d sine theta, where d is constant. D is a constant. We don't know what it is. And lambda, well, lambda's not a constant. That's a number that's changing. So it's d there, and sine theta is constant because it's the same angle. So it's going to be 3 times 600 times 10 to the power minus 9 is going to be equal to 2 times lambda. If you want lambda in nanometers, it'd be times 10 to the power minus 9. Okay? So basically, 3 times 600 is 2 times 400. Is that right? Let me think. No, I've got that wrong, haven't I? Have I misread the question? That doesn't make sense. Which wavelength in the third order spectrum? So that's n is equal to 3, and that's 2. That's why that's a bit strange. So 2 times 600 is 1,200. Divided by the 3 gives you 400 nanometers, B. Okay. Two metal plates are at electrical potentials of 800 and 1300 volts. Okay. Which diagram best represents the electric field strength? So it's going to go, got a positive charge. Well, they're both going to repel on their own. Both plates would repel a positive charge, but this one would repel with a greater force because it's got a larger potential. So the force on a positive charge will always be from the large to the small. So it could be that one, it could be that one. It's not that one, and it's not that one. So it's either A or B. You've got it down to 50-50. Now, if you did your revision, you'll know what shape there should be between parallel plates. We know that theoretically it's uniform, but we know in practice these act like sort of points, these sort of bows outwards. So it's B is your answer. Number 31, got a diagram showing two metal plates with a potential difference of 700 volts between them. Plate Q is earthed, so that's minus 700 volts. What's the magnitude and direction of the electric field at point R? So a positive charge will be upwards, so it'll be towards P. So all the ones saying towards P are possibly correct. That one's definitely wrong. That one's definitely wrong. So now we want to work out electric field strength. Well, that's V over D. So that's going to be a voltage of 700 divided by 0.005. So that comes out to be 1.4 times 10 to the power of 5 newtons per coulomb. Okay, just comes out on your calculator. Now you've got the next one, which is the Nave equation, or I equals NAVQ. I often call it the Nave equation because the way I was taught it. The current in copper wire is given there. What does the symbol V represent? Now it's a velocity, we know that. So it's not voltage, it's not volume, okay? So remember that the particles in a wire, they sort of, as they move, if I take a wire made of atoms, positive ions with a sea of electrons, we know that the electrons sort of go there, they go there, they go there, they might go there, might go back there, down there, across there, down there, and so on. So they sort of drift about, but they gradually move across. So it's going to be the average velocity of those charge carriers, which would be free electrons. 3 resistors connected, oops, try and get that right. Three resistors connected into a circuit with the arrangement shown. And it says the power in any resistor must not be greater than 4.0 watts. What is the maximum voltage that can go across X, Y? So obviously the units are wrong there. Those should be ohms. It's just the way it came out of the machine, so to speak. So we've got to think about it carefully. So we know the current through this arrangement will be the same as the current through this arrangement. So we know that if we've got the current being split here, for the same current, you will have, for the same current, you would have more power being dissipated by this resistor than by these two, because P is equal to I squared R, okay? Now, we want to work out the total voltage across X, Y. So what we've got to do, first of all, is work out the arrangement of the resistors, because we know that that's got to be no more, power in any resistor must not be greater than 4 watts. So you've got to think very, very carefully. So you want to work out the total potential difference across X and Y. Sorry about the disjointedness there, I had to cough. You could tie yourself in knots trying to go through all the formula. You could using power equation, but actually you can do a little bit of inspection. You know the current through here is going to be twice the current flowing through each resistor, okay? If you've got half the current flowing through each one, through each of these, to add up to the total current flowing through here, for the same current flowing through the whole resistor, you could then say, well, okay, if that's the case, as P is equal to I squared R, you'd have each one with dissipated power of power over 4. Okay, so the combined power of the two resistors together would be the total power divided by 2. So what you've got is that to get the total power, that's going to be the power over 2 plus the 4 watts, which is also equal to, so the power through here, 4 watts, divided by the 4 watts here, okay? That makes sense. So the total power is basically 4 plus 2, which is 0.6. Do apologise. I'll start that again because I'm not expressing that very clearly. If you've got the branch here, a parallel branch, half the current, they've got the same resistance, half the current will flow through here and half the current will flow through here. Since the power is proportional to current squared, if you've got half the current, you've got the power divided by 4, okay? So if you take the two combined, you end up with power divided by 2. That's compared to the power dissipated by this resistor, which we know is 4 watts. So the total power of all of the resistors together is going to be the power from this resistor, which is 0.4 watts, So 4.0 watts plus the total power by these two resistors, which would be 2 watts. So that got interrupted again. It seems to be my slightly cursed question, this one. So we've got the total power. We worked out that actually the total power is going to be 6 watts, the total power of the whole combination. So we use P is equal to V squared over R, where we can work out the total resistance. Now you can do this by using a combination of series and parallel formulae, or you can do this by inspection. I think this is okay to do by inspection. So this is 100 and 100 in parallel, so that would be 50 ohms in total. 50 plus 100 is 150. So we know what R is. It's the total R, which is 150. We know P is 6. So if we have V squared is equal to the power times the total resistance, that gives you 900, okay, because 150 ohms multiplied by 6 watts is 900. We then got to square root it, and that gives you 30. So the answer was B, 30 volts. Moving on, hopefully with fewer interruptions this time. Gold is sometimes used to make very small connecting wires in electronic circuits because it doesn't corrode and it's got a really good conductivity. A particular gold wire has got a length of 2.5 times 10 to the minus 3 meters, a cross-sectional area of 6.25 times 10 to the power minus 8 square meters. Gold has a resistivity of 2.3 times 10 to the minus 8. That should be ohm meters. Okay. So want to work out the resistance of the wire. So R is equal to rho L over A. Rho is 2.3 times 10 to the power of minus 8 multiplied by the length of 2.5 times 10 to the minus 3 over the area, which is 6.25 times 10 to the minus 8. No sort of trip ups or anything. No, this is quite straightforward. So the answer comes out to be C, 9.2 times 10 to the power minus 4 ohms. I'm not sure why it changed ohms for the and sign. Right. Now this one, I'm afraid, is not really it didn't really work very well here, but we'll see how we go. Didn't come out the printer very well. So we have a resistor of a resistance of 40 ohms, a variable resistor connected to a battery of electromotive force of 12 volts, and internal resistance of 2 ohms, as shown. So that should be 0 to 40 ohms. It's a variable resistor, so it varies from 0 to 40, and so on. Want to work it, so the resistance of the variable resistor is changed from 0 to 40 ohms. What's the change in the power dissipated by the resistor X? So we're using the idea that it's P equals I squared R, because we don't know the potential difference across X. You could do it by inspection, by working out using a potential divider. You could do it in lots of different ways. So you can decide how to do it. So you can work out the total current when the resistance of all of them is at 0. So when that's at 0, that's going to the total resistance per power is going to be well, we can't really do that very easily, can we? Because yeah, okay. It's probably not the easiest way to do it. So we can stop and think about it. Well, potential divider is probably the easiest way to do it. We want to work out the power dissipated by X. Okay, we could actually work it out using V squared over R. Okay, so we just got to work out what the potential difference across X is when that's 0 and when that's 40. So to work it out, so V1, so V at 0, well, if you've got V at 0, if you've got 40 ohms and 2 ohms, the potential difference, the EMF of 12 volts is shared between them. So it's going to be 40 times potential difference of 12 divided by the sum of the two resistance, which would be 42, which if you get your calculator out, and I'm starting to drown under a pile of paper here because I'm going through notes and all sorts of other things. So it's 40 times 12 divided by 42 should be 11.43 volts. And we know V at 40 is going to be a bit different because here it's going to be still 40 times 12 divided by, well, if we know that, then we can say that that's going to be, we know that's going to be 40, so that'll be 80, 82. So it would be just under half of that. Equals 5.85 volts. Okay. Once you know the potential difference across each one, you can work out the power at 0 by using that one, because you know that is simply 40 ohms. You can work out the power at 40, because that's simply that one, divided by the 40, divided by 40 ohms. Okay, and then you just, and it's the difference between the two. So that's pretty simple, and it comes out to be 2.4 watts. Okay, you can do the calculation yourself for the second half of the lesson. Next one, you've got all the resistors, and these are supposed to be resistors, they're not fuses. I do apologize about it, sort of doing weird things. So it says all resistors here have the same resistance. So which one, so what are they in order of resistance? So this one, of increasing total resistance. So this one, obviously it's got resistance of 0. So A is out straight away. So it's definitely going to start off with X. Now, I think that Z, I think this one didn't photocopy very, didn't come out the printer very well. That's not supposed to be a line in there. So please do discount that from your adding up of your marks. So if we look at this, well, if this is the case, well, if we say each one's got 1, as an example, we have 1 plus 1 is 2, plus 1 plus 1 is 2, so 2 of 2 is 1, so that's going to be 1 ohm. If this is 1, this is 1, this is going to be 1, 1, so that would be 0.5, 1.5. Okay. Bear with me. This is going to be 2 ohms, and this will be 1 ohm, so this will be a half plus 1, which is 1.5, 1 over 1.5. Is 0.67. Okay, I do think that the computer didn't really, that it came out sort of odd on this printer, so I might just ignore this question. So it's going to be, X is going to be the lowest, because even if we discount the lines that are actually in between here, that would be 0.5. Okay, the next lowest would be 0.67. So it's either this one or this one. The next lowest would be, I'll say this one is 1.5. Next lowest would be Z, and the next lowest would be W. So D is the answer. The lines in between there, I apologise about. That's just how it came out of the software. So if we want to work out the total resistance, so the next one, 37, the circuit, the current and the ammeter reading is 0. I think this has not actually come out correctly as well, so I would ignore that one. It's not come out the question generator correctly. Right, ignore that one. So 38, neutron collides with the nucleus of uranium-235. One possible nuclear reaction is shown here. Okay, it's supposed to be a plus. There's something gone very, very wrong with the way this is printed out. One possible nuclear reaction is represented by that equation. X represents 1 or more particles. So what does X represent? Well, we can work it out. So 235 plus 1 is 236. 92 plus 0 is still 92. So it's got to be the same before and after. So 236 got 154 plus 80. is 234. So whatever that's got, it's going to have a mass of 2. The next one is 60 plus 32. Well, that's 92. So it's going to have a charge of 0. So it's got to be a neutron. But the neutrons have got a mass of 1. So basically, it's got to be 2 neutrons. C. The next one is a nucleus. Q as a notation, QY in X. Which of the following is an isotope? So remember, the bottom number stays the same, okay? Because that's your atomic number. So that's not right. That's not right. And that's not right. So 39 has to be A, okay? Because that X number stays the same. And in it's supposed to be beta minus decay, a neutron inside a nucleus changes to a proton. Which statement describes the quark composition of the nucleus during the decay? So if you think about it, a neutron changes to a proton. So neutron is up, down, down, changes to up, up, down, plus the beta minus, even though they put a funny symbol in there, plus an anti-electron neutrino. So what's happened here is that that down quark has changed to an up quark. So the number of down quarks decreases by 1 is the correct answer, but just double check. Number of down quarks increases by 1, that's clearly not right. Number of down quarks stays the same, not correct. Number of up quarks stays the same, not correct, because it's increased by 1. So the answer is A. So as you're going through that, you can recalculate your score, but basically ignore question 37 because that came out the print, well, 36 and 37, because they both came out the printer in a very, very strange way when they sort of went uploaded to show my homework. So in the meantime, please make sure that you've got your corrections done, and make sure you understand why. And next week we'll do the walkthrough for the written answer paper.